answered it at the same time. We got the p-value, pull them both at the same time. I could be wrong. We have to, wouldn't we?
Isn't that the one where we did p hat minus p equals
Yes, ma'am.
negative 0.019?
1,9 and then over the root pq over n, and then that, the result of that.
You want to write this down?
That, right, Jolene, that is, thank you for that, that is the test statistic, whatever the value of that calculation is. Z, yes ma'am. Z equals whatever that equals. Yeah, whatever that numerical value is. Now what I want to do today is, I want to revisit that p-value before doing more, because I think I have 3 more tests I want to do today. 3 more hypothesis tests on proportions that I want to do with you guys today. Then next class, we'll move into the world of averages. And then we'll just keep switching gears day to day, proportions, averages, proportions, averages. And that's, once, again, you understand kind of how the template works and how the parts of a test go together, it'll be more rapid. We won't have to take, I think it took us an hour and a half to get through that template, and it was time well spent. Not everyone will be an hour and a half, I promise you that. It won't be that slow. So, and that's okay though, I don't mind the time, I think the time is important. Let me get into here though, and call up, yeah, over here, and what I want to do is, I want to open up, will it open, or will I have to click it from the inside? Yeah, this will work. So, real quick, I want to revisit the p-value. And I want to give you a bit of an indicator of what I want to make a quiz for you guys for next week based on this spreadsheet. So, what we did was, we put ourselves in the place of a researcher developing a flu vaccine. And what was the whole point of the test we did on Thursday? What was the whole point of that hypothesis? I keep saying test, the hypothesis test, the template we filled out. What was the point of that template?
To see if the vaccine reduced the incidence of poisoning.
And I love the way you said that. You didn't just say to see if the vaccine worked. You defined what worked was. Did the vaccine reduce the incidence of the flu? Good. How did we define reducing the incidence of the flu?
It appears that it did.
Well, but how do we define it? The conclusion we had, I believe, was it appears that it did.
It's less than 12%.
Oh, good. That's how we defined it. It was working. If the flu vaccine came in at less than 12%. Less than 12%. Now, why did we pick 12%? Was that out of the air?
No, that was the control group.
Yes. So, and that number is gotten from where? I'm assuming. Where do you think that number came from? I told it to you, but where do you think it came from?
Statistically from the population.
From the population, CDC, for a given area, local CDC chapter. Absolutely. Somehow, it's known that 12% of people get sick. Now, I say known, there's no margin of error attached to that, which is slightly suspect, of course. There should be a margin of error, but none was given. Surprise. And that's one of the limitations of this, is that 12%, technically speaking, should have a plus or minus, but it doesn't. So the assumption I have is they've done hundreds of thousands of studies, and what has happened with the margin of error? Essentially, it's shrunken down to a point. You can imagine that with this kind of studies we're doing here, they've shrunken down to a point. So they can basically call them parameters and call it good. Now Melanie's looking at me like, but that's not right. You're right, it's not right. It's not. That's why I like 2 sample testing better when you have a pure control group and a pure experimental group, rather than an experimental group and some parameter that we're testing against. I do like that better.
Well, and I have a question because we said that it showed that it was likely to be effective, but we didn't round. It was like 11 point something that would have rounded to 12.
What was 11 point? I'm not following that.
Or, I can't remember, whatever the outcome we had with the vaccine, we didn't round it to...
What was the test statistic we got? Do you remember? I don't remember.
Negative 1.8.
Negative 1.85, which carried a p-value of about 3%, 3 point something percent. Good. Okay. So Veronica, hold that, if you would, hold that thought. I love what you're saying.
Okay.
And it harkens up to the problem with having a cutoff. What magical number are we looking for in cases? What is that magical p-value number that if we get below we say, aha! 5%. Why 5%? You can't remember. You can't remember because it's the rule and it's not a very good one. Here's the thing. 5% is historically, and please YouTube world hear this, Fisher created the p-value 100 years ago and said, why did the statistician Fisher create the p-value? What did he say a small p-value means? What should you do? Say it again, nice and loud. Emily, thank you. Take a second look. That was what a small p-value was. Like, oh, that wasn't expected. Because what is something that's not expected? Sometimes purely an outlier. It might have been random fluky chance. It might have also been that something changed and you saw a change. So a second look will kind of drive that point home. If we take a second look and it's fluky a second time, then it's less likely to have been an outlier, yes? Because getting an outlier once is a 1 in 20 shot by definition of bell curve. Getting an outlier twice is a 1 in 400 shot by definition of a bell curve, right? 1 in 20 squared. Because if it's really outliers, and they're independent of each other, 1 in 20 times 1 in 20. So 1 in 400 is not going to happen, but once every 400 times, so it shouldn't happen a second time. So if it does happen a second time, you go, oh, maybe we found something cool. That's the point of replication, again. So, back. 5%, we're looking for 5%. So we came in at 3%, yes? What I want to do real quick is I want to analyze that 3% in another way. What I've done here is I set up a spreadsheet. How many of you guys did the quiz on the black deck of cards a few weeks ago, testing my black deck, another look at my black deck of cards, the ones you said, oh, that card, that's rigged, there's no red cards in there. Good for you. I made a similar spreadsheet, less colorful, because I didn't know how to color the flu. And I started, but I made it green and chunky, and that's kind of disgusting. So I put 1,000 people, which was the size of our sample. Remember, our sample in this study was 1,000 people. So if you scroll across this, you'll see 1,000 people. Okay? Now what I've done in each of those cells, I want you to look at that command and see if you can process what that command is doing. Like I said, I'm going to have a quiz built around this so you can look at it again more carefully. It says, if rand between 1 comma 100 is less than or equal to 12, then write flu. Otherwise, write no flu. Where does 12 come from?
The percentage.
12 comes from the general population. 12 in 100 people are going to get the flu. What I'm doing is I'm randomly assigning 12% of my 1,000 the flu by using random numbers. I'm rolling, if you will, a 100-sided die. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, they get the flu if they roll those. If they roll 13 through 100, they don't get the flu. Isn't that 12%? 12 out of 100. Make sense? Hopefully. Now, will it be exactly 12% every time? Of course not. We have sampling error, but it should be close to 12% every time. Close to 12% every time. Now, what does close mean? That's the point of the hypothesis. Well, on average, yes. On average, absolutely. But the plus or minus, how close is close enough? We get the average for free, but the tightness of the curve is going to vary. So what I'm going to do is, right now, in this, I'm going to hit F9, let it reload here. But right now, 109 people out of the 1,000 got the flu. You can see it up here. It says number that got the flu, 109. What it's doing is it's going through this line right here and counting all the incidences of the word flu. So right now, I sampled 1,000 people. 109 got the flu. Yeah, 109 got the flu. So what percent is that? 10.9%, yes? That's 10.9%, 109 out of 1,000. So, what do we say? How do we say if we say the vaccine is working or not? I don't know. Let's check it again. F9 again. 121 got sick this time. What's that? That's 12.1. So what I'm going to do is, I have my stapler with me. Something heavy with me. There we go. I'm going to let Excel. There we go. What it's doing right now is it's testing 12% in the general population. It's saying, okay, let's assume 12% of people get sick. If I grab them 1,000 at a time, what would that actually look like? What would that actually look like? So what we're doing is, you can see them flip-flopping, it's changing constantly, and very quickly actually. So you're replicating a study over and over and over again, essentially, by randomness. So you're building your null curve. Now I didn't draw the curve, and that's something I'm going to add to the quiz for you guys for next week, is actually adding the curve right in here. I ran out of time, unfortunately, to get to that. Linda?
So the cases is at the 1,000 people, how many times you've done this?
That's right here, total number of trials. Every time this goes up by 1, I'm checking 1,000 more people.
Okay, so
yeah, so I've checked like 1.5 million people by now.
Okay.
But what do you notice has happened? Look at right above that. Thank you, Linda, for noticing.
That's
Look,
what I was wondering about, like, where it says the cases.
look right above that. Number of cases where 101 or fewer folks got the flu. Is that happening very often? It seems to be changing, but not changing super rapidly, yes? Not changing super rapidly. As a matter of fact, I've got a percentage down here of how often it happens percentage-wise. It's happened around 2.82, it's fluctuating a little bit, it's happened right around 3%. And if we let this thing run, which I'll let it run as long as we can, it's going to eventually stabilize if we let it go long enough. So we'll let it play here. It's going back up again now. It's going back down. It's hovering right around 3%. Right around 3%. Does that sound familiar? Right around 3%? McKenna, where did we hear that before? Remember when we ran the actual test statistic and we got negative 1.85 and then we shaded that area to the left of that and we came up with essentially the same exact area? Now it's off by 100th or two right now, but it's stabilizing. Is that a coincidence?
No.
Hell no. I call this step 11 of the hypothesis test. Number one, because I'm a Spinal Tap fan. But number two, because you don't need to run that entire hypothesis test if you can just set up a simulation like this. This shows how unlikely it is to have seen the 101 cases that we saw. Now, why is it 101 or fewer, do you think? And this, verbalize this now, this is what the quiz is going to be on. Why is it 101 or fewer? Good. And Linda's like, that's what I was thinking too. I was wondering why it's 101 or fewer. Jolene?
Could it be setting up a standard deviation?
Essentially, yes.
Okay.
It's exactly what it is. The idea is, if you have 1,000 people that you're getting sick, or that could potentially get sick, there are 1,001 possibilities for the number of those that got sick. Anywhere from 0 up to 1,000. The probability of any one of those events is essentially 0 because there's so many of them added together to be 100%. So when you're looking to see how extreme the 101 that you guys got was, how extreme it is, when I say how extreme, you're trying to see where it lives on the curve. Is it near the middle or is it outside in the standard deviations? You kind of want to go use your 101, your sample results as a baseline, and then shade the ones that are even more extreme. Because if you're testing a flu vaccine, you got 101, you'd also want to include the more extreme cases where you got even lower, which would be fewer people sick. So you're trying to calculate the extremity of those values. That's the only fair way to do it. The chance of getting exactly 101 is essentially 0, but you have to get 101 or fewer. Kendra, please.
Okay, so this is obviously with no vaccine, so the 3% is 3% of those people got less than that, so that's why there's a 3% chance of the vaccine.
May I restate that? I love what you just said. And I want to make sure we restate it properly. What we just said, and the curve will make this much more, oh, look how close it is to our value now. What do we get for our p-value? 3.1%? 3.2, it's a little bit above, but it's creeping back down again. It's going to stabilize. So what I'm going to do, Kendra, let me draw a curve to go along with this. But this is what the Excel sheet will look like next week for you when I get this quiz made.
I think I'm confused on where it says the number of cases 100.
Don't worry. I'm going to draw a picture so it'll help it right now. And like I said, I'm going to have a quiz on this too. And that'll drive it home because I'll have you guys exploring this just like we're doing right now. So, Kendra, you said correctly, perfectly, your null curve is centered at 12%. This is the same curve we drew last week. And we also called it 0 for the 0, you know, and then the idea is where did our sample result land? So our sample result was 101 out of 1,000, which is 10.1%. So we landed down here somewhere. The question is, how far down there by standard deviations? Is 10.1 right here? Is 10.1 right here? I think Natasha last week used the word ruler or something like that, was how far down, you know, depending on how squishy or how loose the curve is, it's going to govern where the 10.1 falls. So I'm going to put it down here, 10.1%. Now the question mark that goes right there is, what is that? Now we calculated that last week at negative 1.85. That's what we calculated. So we know that that z right there is negative 1.85. The thing is, what's the chance of landing exactly at negative 1.85? Infinitely small. I mean, if you think about it, the whole curve, if I shaded the whole curve, yes? If I shaded the whole curve, what area have I shaded? 100%. This is a 243 question. If I shade the entire bell curve, begin left to right, and I say left to right somewhat comically because it's infinitely left and infinitely right. I've shaded 100% of the curve, right? The problem is, any vertical line I draw, there are infinitely many of those vertical lines, yes?
Yeah.
So any one of them has no area. So in order to calculate how extreme this is, if you're trying to look at the effectiveness of a vaccine or the effectiveness of a regimen, we'll see all this momentarily. What you want to see is, if 10.1% was the result in your sample, what's the chance of being at least that far away from your assumed center? And what is at least that far? That far or further or larger or further away. Larger is kind of loosely into the tails, essentially. You want to go into the tails because that's the chance of being that far or further. And that's why we ended up adding all these lines in. But here's the kicker. Hold that question out. I love what you're going to say. The kicker is, even when we add all of that area in, what does it add up to? Not very much. Not very much. Which still doesn't change our belief. Does it look like our vaccine belongs on this curve? Does it look like our result belongs on this curve if we're only shading 3.3% or so? Nope. Our belief goes that it's most likely on some other curve that's lower. Does that make sense? It's related to what you said. I wanted to make sure that you don't want to say, and this is a common mistake people make with the p-value, and I don't mean right now, we're learning. Of course I want you to say that. But you can't say things like, there's a 3.3% chance the vaccine is working, or there's a 3.3% chance the vaccine is not working. That chance, that p-value is tied strictly to your sample. What it makes you say is, holy crap, we were assuming the vaccine was ineffective. If the vaccine's ineffective, we're on this curve. That p-value is very small. I don't think we're on the curve anymore. You don't actually quote the p-value in the conclusion, the verbal conclusion. You just say, it appears the vaccine is lowering flu rates. Does that make sense? No, I love what you said. It's a very, very important thing to do right now. Because if we do the experiment again, are we going to get that same p-value? Well, you're seeing it. The answer is no. Right? This is the answer. The answer is no. You're not going to get the same p-value. You get a different one every time because you get the different number. Well, of course, it's included by the wall right there. I can't read that fast. But it's changing every single time, yes? So the p-value, I'm sorry, what was our p-value again? 0.33 what? 0.322. Okay, so we're still a smidge above, but it's on its way. But that's the idea. It's constantly shifting. So you don't ever want to quote the p-value as part of your conclusion. What you'll often see in the literature, though, is, in parentheses, the p-value stated as support for your conclusion. And that's the whole point. That's
less than 5.
And again, less than 5. That's the general cut. Do you remember one reason? Well, we'll go back to that. I'm going to get off that question. Alan, go. Your question.
I think you just answered it. Because
Maybe.
I was curious if the p-value is 3% and that's ineffective, that means 97% is effective, and I was curious where the 12% fell in that.
This goes back to Kendra's question, actually. And the 97% is just as transient as the 3% is, if you think about it. The big idea is we've escaped a 95% confidence interval. 97% is bigger than 95, so we've escaped the interval. So the idea is and this is actually called the classic treatment of hypothesis testing. What people will do is they'll come out here and they'll slap what's called a critical value, and they'll demarcate where 5% starts. Now you might remember this from 243, it's okay if you don't. That is negative 1.645. That z-score demarcates the end of 95% and the beginning of 5%. Fair enough so far? So the 97, all that means is we're 2% past that critical value, which means we're into what is classically called the rejection region. And all that means is we reject H0. H0, the null hypothesis says the vaccine was ineffective. We reject that. I don't like saying that. I'd rather be positive and say it appears the vaccine's working. But, of course, Fisher would tell us to go and do it again and see if it works a second time.
How many times should you do it?
Well, the more the better. I mean, it's probability. There's always a chance you can get an outlier twice, it's 1 in 400. But think about how many studies are done a year. Way more than 400, yes. Right? Way more, and 400 replicated studies. So even one of those is going to generate 2 false positives. The more the merrier. The more the merrier. Now, of course, you're going to get eventually an outlier result running those. Right? On average, every 20, you're going to get an outlier result based on bell curve behavior. But that's the idea. You're generally not going to get it on the first one or even the first 2. You're going to get it spread throughout 20. You guys are asking really awesome core questions. Please keep asking. Veronica, yes?
So this kind of goes back to the multiple CIs. If I do the same exact study, can I combine the numbers, or do I have to look at the confidence intervals? And
As
go
long as you
back
do the
to-
study in the exact same way with the exact same constraints, absolutely. It's
Okay.
essentially doing the study a second time, even if you're a totally different body of work, whatever. Yes, absolutely.
So where we get into having to multiply those by that power, like we did,
Yes.
is when there's disparate studies that aren't the
Exactly,
same.
exactly, which is why we don't like doing that.
Gotcha.
We don't like doing that because we lower confidence.
Okay.
Speaking of lowering confidence and your question from earlier, Veronica, I just realized we're never going to get this to equal 3.2%. Not because of a statistical reason, I just thought of something. It's a question you had earlier. Our test statistic wasn't negative 1.85. We rounded that, didn't we? We rounded that. It wasn't down that far. It was 1.84 and some change, if I remember correctly. Now, don't worry about if you don't have it. We're going to show you the shortcut to get it right now on the TI. It's actually a little bit further this way, because we rounded it to the 2 decimals, which means we're going to have a little bit more area than we calculated before. Yeah?
So the bell curving, we know that that's on another bell curve.
Well, we think, we don't, careful with the word no, right? This is implying that it is. We could still be wrong, yes? Does that make sense? I always want to say that because the course is probability. This makes it look, it appears as though there's another curve, yes. I didn't mean to jump down your throat like that. I just want to make sure, we want to get away from saying things like no and prove, because there's some uncertainty, yes?
So then how do you know if
You never do. That's what's so frustrating, I think, to students, is that you never know if you're right or wrong. The only way you'd know if you were right or wrong is if you sample the entire population. But you never can do that. So you're getting these snapshots, which is why with more replication, you're getting a bigger and bigger chunk of the population snapshotted.
Because if you keep getting those scores, the probability that
Of them all being wrong, yeah, shrinks to 0, so the chance of at least one of them, exactly. Which I had you guys calculate on your exam just recently. Then. Remember when you did 51 confidence intervals? It shrunk to 7% likelihood that they're all correct? That's terrible. But that's the idea, though. The chance of them all being wrong is also terrible, but that's a good thing. That's a good thing. Linda Fair? Jolene, good follow-up. Now, this is great, except we're not usually carting around Excel in our back pocket, which is unfortunate. Soon, we're getting there with smartphones. I love that technology. Let's make sure we can run the shortcut in here as well, yes? Let's make sure, I did this very quickly at the end of class on Thursday, and I want to make sure that you can do it as well.
Oh, I still don't know.
Well, good, you might still have it independent.